Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are beginning a very important discussion on Huygens Principle from Unit 10, Wave Optics. And we promise a simple exam-safe explanation that, even the weakest student can understand. Okay, let's start with a simple question. When you see ocean waves hit a harbor, opening, a gap in the wall, why don't they just stop? Why do they bend and spread into the harbor, even behind the wall?
That is a very interesting question. I always thought waves just travel straight, like light. Why would a water wave bend like that?
Exactly. That's straight line travel. That is geometrical optics. But this bending is wave optics. Now, here's a surprising example that really shows this. If you take a laser and shine it past a tiny object, say, a razor blade edge, you would expect to see a very sharp shadow behind it.
Of course, a dark region where the light is blocked.
Right, but what if I told you that you might see a tiny bright spot right in the middle of that dark shadow?
Wait, what? A bright spot in the shadow? That is completely counterintuitive. How can light go into a dark region and still create brightness?
Precisely. And this is where Huygens Principle comes in. It explains all of this. Okay, let's unpack this. The core idea is actually simple. Huygens said, forget the original source for a minute. Instead, think of every point the wave has already reached as a tiny new source of waves.
So instead of one wave expanding, it's like it's constantly recreating itself as it moves forward.
That's a perfect way to put it. It's a kind of self-regeneration. Let's use our primary analogy for this, the ripple ring model. When you drop a pebble in a still pond, a circular ripple expands outwards.
Yes, simple.
Now imagine that every single point on the perimeter of that expanding circle suddenly drops its own tiny pebble, all at the same time.
Okay, so millions of tiny ripples starting from the edge of the first one. That sounds like a lot of work.
It does, but that's the beauty of it. The outer boundary that is formed by the tangent or the envelope of all these tiny ripples, that becomes the new wavefront.
Ah, I see. So it's not one big wave moving, it's millions of tiny waves combining to look like one big wave moving forward.
Exactly. And this concept exists because geometric optics only gives us the laws, like Snell's law. It tells us what happens. But Huygens gives us the mechanism. It shows how wave propagation necessarily produces these laws. It's the key to understanding reflection, refraction, and diffraction. Now let's build a strong mental image for refraction. Picture a line of fence slats, or maybe soldiers marching in a line on a smooth pavement. They're approaching a patch of mud at an angle. The mud is our slower medium.
Okay, I can picture that.
The moment the first slat hits the mud, it slows down, right? But the other end is still on the pavement, moving fast. To stay connected, what must the whole line do?
Oh, it has to rotate. The fast end will swing around a bit as the slow end drags. The whole line has to turn.
Precisely. That rotation is the new angle. The wavefront rotates because the secondary wavelets in the slower medium, the mud, travel less distance in the same amount of time. Now, let us see how NSERT formally defines this concept. This is the definition you must write in your exams. Could you please read the definition of a wavefront for us?
Of course. It says, a wavefront is defined as a surface of constant phase. The speed with which the wavefront moves outwards from the source is called the speed of the wave. The energy of the wave travels in a direction perpendicular to the wavefront.
Excellent. And now for the principle itself.
For the principle, it says, each point of the wavefront is the source of a secondary disturbance, and the wavelets emanating from these points spread out in all directions with the speed of the wave. If we draw a common tangent to all these spheres, we obtain the new position of the wavefront at a later time.
Perfect. Those two ideas, the surface of constant phase and the secondary wavelets forming a new envelope, are critical. So let's just break down the formal steps of propagation. Step 1. We start with a wavefront, let's call it F1, F2, at time p equals 0. Step 2. Every point on this wavefront, F1, F2, acts as a secondary source.
The tiny pebbles again.
Exactly. Step 3. From each of these points, we draw spheres, the secondary wavelets, and the radius of these spheres is v times t.
Where v is the wave speed and t is the time.
Correct. And step 4, the final new wavefront, G1, G2, is the envelope, which is just the common tangent to all these spheres. Hope everything is clear so far. This concept explainer is from ProfSam.com, that is ProfSam.com. Now let's do a quick worked example. If a plane wave with a wavelength of, say, 500 nanometers passes through a single slit of width 10 micrometers, we want to find the angle theta where the first dark fringe appears.
Okay.
Using Huygens' idea, the top half of the slit cancels the bottom half when the path difference, which is a sine theta, equals exactly lambda.
Oh, I see. So sine theta is just lambda divided by a.
Yes, just plug in the numbers. 500 times 10⁻⁹ divided by 10 times 10⁻⁶ gives you 0.05. This means the light bends outward very slightly, about 2.87 degrees. This shows how Huygens' principle applied across an opening leads directly to the diffraction formula.
Ah, okay. So even in that tiny opening, the light still acts as millions of tiny sources, and they cancel each other out at specific angles to create darkness.
Precisely. And connecting this to the next topic, this entire idea of wave propagation and the envelope construction is what we use to formally derive Snell's law and the law of reflection. Now, let us address 3 common mistakes, the silent killers that lose marks in exams. The first one is that many students think the wavelets travel backward as much as forward.
But wait, the definition I read said wavelets spread out in all directions, so shouldn't there be a backward wave too?
That is an excellent question. And the insert wording is a bit misleading. The secondary wavelets do radiate in all directions, yes. But the envelope of all these wavelets only constructively adds up in the forward direction. Huygens himself had to just make an assumption about this, but the rigorous wave theory confirms the geometry actually cancels out any backward radiation.
So only the forward-pointing wavelets add up constructively. Got it. No back wave.
Perfect. Second misconception. Students sometimes think Huygens' principle only applies to light.
Well, we do learn it in the wave optics chapter.
True, but remember the principle is universal. It applies to all waves. Sound waves, water waves, radio waves, or light waves. The physics is identical. And the third one. Students confuse the principle with its application. They might say that Huygens' principle causes reflection or refraction.
But it doesn't.
No. The principle is the mechanism. It is the specific boundary conditions, hitting a mirror versus hitting glass, that determine whether the resulting envelope will be a reflected wavefront or a refracted wavefront. It's the tool, not the result itself. Okay, to lock this idea into your memory, let us use some anchors. The catchy phrase is, every point on the wavefront is a speaker. The combined sound is what you hear forward. And for a physical gesture, imagine standing in line with your friends. That's the wavefront. Now, at the sound of a clap, every person must face forward and shout at the same time. Those shouts are the secondary wavelets. The combined sound you all hear forward is the new, smooth wavefront. And finally, a mnemonic to remember the core steps of this entire unit is WHIPW for wave, H for Huygens, I for interference, and P for polarization. Huygens is the key to understanding the H. Okay, let us summarize the 3 factual takeaways about Huygens' principle that you must remember for your exams. Point 1. Huygens' principle states that every point on a wavefront acts as a source of secondary wavelets, and a new wavefront is formed by the forward envelope, or the common tangent of these wavelets. Point 2. The principle provides the mechanism for understanding how light propagates. It lets us derive the laws of reflection and refraction, which purely geometric optics cannot explain. And point 3. Huygens' principle is universally applicable to all types of waves, sound, water, light, and it's the foundation for explaining interference and diffraction phenomena. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Study hard and all the best.